All right. So, chapter 6, lesson 6.6, this is general probability rules. General probability rules. I have two formulas for you guys today. Two formulas to start you off today. Before we do that, a couple of reminders of our old formulas. All right. So, let me do this in red. So, reminders, review of old formulas. The first one is the probability of A given B. That's the probability of A and B over the probability of B. All right, so that was our conditional probability formula. This was lesson 6.4. And then to test for independence, A and B are independent events if the probability of A given B is equal to the probability of A. All right, so hopefully you guys kind of remember that. Quick refresher from our lessons last week, our last week lessons, okay? All right, so we're gonna add two more formulas to this, All right, now before we do that, a couple of things to kind of set up, all right? The first one is talking about sampling with replacement versus without replacement. So for example, I don't know if you guys like playing cards or anything, but let's say you have a standard deck and you're gonna pick two cards. There's actually two ways to do this, to pick cards from a deck. You can pick a card at random, look at it, replace the card, shuffle it, and then pick another card. So that's sampling with replacement. Now, why that's important is because the first pick, right, the first card you get won't affect what the second card you get is, right? Because it's almost like you're starting out with a brand new deck on the second draw since you replaced the first card. However, there's another way you can do it. You can actually pick a card, not replace it, and then pick a second card. That's sampling without replacement. And in this case, the events are dependent because the second draw, right, is affected by that first draw. Okay, so let me give you an example of how this affects how you find probability, okay? So let's say I pick two cards from a standard deck without replacement. And I want to figure out, well, what's the probability that I select two spades? So I don't know if you guys know cards at all, but there are 13 spades in a deck of 52 cards. All right, 13 spades out of 52 total cards. So the probability I get one spade is pretty straightforward, right? It's just 13 out of 52. But now that I'm not putting that spade back, when I draw the second card, right, that one spade is out. So now I have 12 spades left out of 51 cards that are left. So then this is the setup for the probability. Okay, so just really quickly to show you what I had before. The events are not independent since I'm not replacing the card. And so the probability of E and E2, right, drawing the first spade and the second spade, is now 13 out of 52. The probability of the first card is a spade times the probability that the second card is a spade given the first card was a spade. And that's why it dropped down to 12 over 51, which is 1 over 17. Okay, let me take a pause. Any questions about that example? Okay, well, this leads us to our first formula then. So this is the general rule for multiplication. For any two events, A and B, any two events, this is your formula now for probability of A and B. All right, probability of A and B. This will be the probability of A times the probability that B happens given A has already occurred. All right, so this, like tying this to our example, the probability of the first being a spade and the second being a spade is the probability the first card was a spade, 13 out of 52, times the probability that the second card was a spade, given the first was a spade. So that's 12 over 51. All right, any questions about this formula? All right, so let me break this down and you guys can feel free to screenshot this mind map that I'm going to show you, or you can just kind of do a sketch of it to the right of this formula on your notes. There's a little bit of space there, okay? So this is your thought process, all right? This is the thought process whenever you're trying to calculate the intersection of two or more events, meaning you want to find the probability of A and B, keyword being and. This should be your thought process. First question you should ask yourself, are these events independent? Are these events independent? Are A and B independent? Does one affect the other? All right. If the answer is yes, they are independent, meaning they don't have any effect on each other, then I just do the probability of A times the probability of B. An example of that would be like drawing a spade from a deck of cards and rolling an even number on a die. What you draw doesn't affect what you roll, right? So those are independent. So I would just multiply probability of getting a spade, probability of getting an even, and just multiply. All right, if the answer is no though, right, like drawing two spades, right, the events are not independent, then you want to use the general formula, probability of A times the probability of B given A. All right, so this is your mind map. If you want to take a screenshot, go ahead and do that now. Or you can just kind of copy this down on your notes. And any questions while people are doing that? Okay, well, let me show you guys an example of how this kind of works out. All right, so I'm going to give you an example of how I would use this mind map. So here's our example. If anybody needed me to go back, just let me know. Okay. Let's see, Leong, can you read this one out for us, please?
There are 7 girls and 8 boys in a math class. The teacher selects 2 students at random to answer questions on the board. What is the probability that both students are girls?
Thank you. All right, thanks, Leong. So basically, I want to find the probability of a girl and then another girl. All right, so first pick girl and second pick girl. Okay, so this is clearly an and problem. So my first question is, are these events independent? So think about that. All right, are the events independent? First one being a girl, and then the second one being a girl. Well, in my mind, I'm thinking, well, is she sampling with replacement or not? In this case, if you're selecting 2 students to answer questions on the board, typically it's 2 different students, right? So you're not sampling with replacement. So I would say that the events are not independent, right? First girl chosen and that girl's out, kind of like when you're drawing a card and you don't put it back in. So if that's the case, then I want to do the probability of first one being girl, 7 out of 15, times the probability that the second person is a girl, given the first one was a girl. And so that brings it down to 6 over 14. All right, if the teacher sampled and, with replacement and the events were independent, I would do 7 over 15 times 7 over 15. But since they're not, she wants to pick 2 different girls, then that's why this is the probability. All right, any questions about that? All right, well, let me do one more example before we get into our second and last formula for today. So this question about light bulbs. Luca, can you read this one out for us, please?
Suppose let me minimize the faces.
Oh, yeah, no problem.
Suppose the manufacturer of a certain brand of light bulbs made 10,000 of these bulbs and 500 are defective. You randomly pick two such bulbs off the shelf of a store. What is the probability that both bulbs are defective?
Awesome.
Are the selections independent?
Oh, yes, sorry. Yes, thank you. Okay, so the first question is, yeah, this is an and problem once again. Probability that the first one is defective and the second one is defective. So the first question you want to ask yourself is, are the selections independent? Well, in this case, there are 10,000 light bulbs. 10,000. If you pick one off the shelf, does that really change anything? Slightly, yeah. It's out of 9,999 now. Your denominator slightly changes. But because it's such a big group and you're only picking one, it really doesn't impact the 10,000, right? So in this case, when you have a big population like this, we actually can assume that it's practically independent since there's so many bulbs. All right, so when you see a big population like this, you can actually just assume, yeah, this is pretty much independent since I'm sampling from such a big group. All right, so the probability of defective and defective is just going to be 500 over 10,000, right, which is 0.05 times 0.05 again. All right, and then we get an answer of 0.0025. All right, let me take a pause on our second example. Any questions?
I'm like kind of confused how to tell if it's independent.
Yeah, so basically you just want to ask yourself, does my first pick affect my second pick, right? Does my first event affect my second event? So the card example, when I picked a spade, right, and I didn't replace it, the deck is now out of 51 cards instead of 52 cards, right? So that actually does make a pretty significant difference. If you calculate, let me do that real quick. 13 out of 52 is 0.25. All right, 12 over 51 is 0.23. So it made a pretty significant change, right? But if I'm doing, 500 over 10,000, that's 0.05. And I do 499 divided by 9,999, that's 0.0499. So I don't know if you guys can see that, but it didn't change that probability that much. So that's why we said, oh, it's practically independent because there's just so many bulbs. If I take one and I don't put it back, it's not that big of a deal. But for cards, there's only 52. So if you take one out, that actually significantly changes things. Does that answer that question, Margot?
Yeah, thank you.
Okay. All right, any other questions on that? That's a great question because that's the first question you want to ask yourself when you have a problem involving and. That's okay. Okay, all right, let's do one more of this one. This one's a little bit tougher. All right, this is a little bit tougher. Same situation. All right, 5% of the time there's a light bulb that's defective. And then we pick two packages. This question is, what's the probability that exactly one bulb is defective out of the two picks? What is the probability that exactly one bulb is defective out of those two picks? Okay. The reason why this is a little trickier is because if we want exactly one bulb defective, there's more than one way that can happen. Now, here's my advice. When it comes to probability problems, you really want to break it down to like what specifically can happen. And I think one of the best ways to do that is to do a tree diagram. All right, to do a tree diagram. So I made one here for you guys for this case. So this first branch, right, set of branches is what happens with bulb 1. All right, so bulb 1 could be defective, and there's a 5% chance of that happening, 0.05. And so bulb 1 not being defective, there's a 95% chance of that happening. All right, so that's my first branch for bulb 1. For bulb 2, right, if bulb 1 is defective, there's still a 5% chance that bulb 2 is defective, and there's a 95% chance bulb 2 is not defective. If bulb 1 is not defective, still 5% chance that bulb 2 is defective, 95% chance bulb 2 is not defective. Let me take a pause. Any questions on the tree diagram that I built for this? Okay, I think this is a great first step for this because when it comes to a more complicated problem like this, it's better to see all the possibilities and then pick out what you need. So we want to figure out what's the probability that exactly one of these is defective. Okay, so here is what I would do. I'm going to highlight, oops. Oh, sorry, hold on one sec. Can you guys still hear me? Okay, cool. So what I would do is I would look at, there's 4 branches that, go out at the end, right? 1, 2, 3, 4. And so I'm going to focus on where I get exactly 1 defective bulb. So if bulb 1 is defective, then bulb 2 must not be defective. So I'm looking at this branch. If bulb 1 is not defective, bulb 2 must be defective. So I'm looking at this branch. All right, so these are the 2 ways I can get exactly 1 defective bulb, exactly 1 defective bulb. So to calculate this, I would go 0.05 times 0.95 and add that to 0.95 times 0.05, right? First bulb is defective and second bulb not defective, or the first bulb is not defective and the second bulb is defective. So that would be my solution. Okay, I'm sure, oops, sorry. I'm sure there's questions on this one. Questions? Oops, sorry. Sorry, give me one sec, guys. Here we go. Okay, so our next formula for today, general rule for addition. So we had a general rule for multiplication. That was our and. This is now or. All right, this is now or. So for any 2 events, E and F, all right, the probability of E or F is the probability of E plus the probability of F minus the probability of E and F. All right, so this is your second formula. All right, so just to kind of make sense of this, look at a Venn diagram, okay? If I want the probability of E or F, I want everything shaded inside either E or F, right? This whole area right here. So I would take the probability of E, and that's this shaded area, plus the probability of F. Now, if you notice, when I did that, I counted that middle part twice. That middle part got shaded twice. So because of that, we need to subtract that intersection. And that's why this formula is the way it is. Okay, so again, probability of E plus the probability of F minus that intersection since it got counted twice. All right, here is your mind, or excuse me, I will give you a mind map in just a sec, but give me, let me show you this one quick example first. All right, and let me get Margot, can you read this one for us?
Yeah. Musical styles other than rock and pop are becoming more popular. A survey of college students finds that the probability that they like country music is 0.40. The probability that they like jazz is 0.30, and that they liked both is 0.10. What is the probability that they like country or jazz?
Awesome. Because yeah, I'm sure all teenagers, enjoy a good jazz music session. So this question is different because now we're asking or. All right, so always look at what word is kind of happening there, and or. In this case, it's or. So I'm going to use that formula for country or jazz. So that's the probability of country plus the probability of jazz minus the probability of country and jazz. In this case, they give us all those numbers. So country probability of country music, 0.4, jazz, 0.3, probability they like both is 0.1. So 0.4 plus 0.3 minus 0.1 gets you 0.6. So 60% chance that somebody likes country or jazz. All right, questions on this one? Okay, so here is your mind map. Okay, so when you're trying to find the union of two events, E or F, the first question you should ask yourself is, are the events mutually exclusive? All right, and just a reminder, mutually exclusive means that there is no intersection. So when you do your Venn diagram, it's actually two separate circles. All right, if the answer is yes. If the answer is yes, and there's no intersection, you can just do the probability of E plus the probability of F. Right? So this was like our Toyota, Nissan, and Honda example from before. We had disjoint events, mutually exclusive events. There's no intersection, so you can just do probability of E plus the probability of F. If the answer is no, then you need to subtract out the intersection since it exists. All right, now here's a follow-up. In some problems, the intersection is given, right? Kind of like our country jazz example. They just give you that. In some problems, they don't give that to you. So you need to find that. Now you can use the first formula from today to find that, right? If independent, that's just the probability of E times the probability of F. If not, then you use the formula we learned at the beginning of this lesson. All right, so this is your mind map for the union of two events. Go ahead and you can screenshot this or jot that down in your notes. Got some room on the side of that Venn diagram for you. All right, any questions? Make sure you say it out. Don't leave it in the chat because it's actually hard for me to see the chat because my PowerPoint kind of overtakes everything.
Well, do you need to explain again why you have to subtract the intersection?
Yeah, I think it makes the most sense with the Venn diagram, right? So if I want to find the probability of E or F, it's this whole region inside either E or F, right? So if I want to find this region right here, I can take the probability of E, this shaded region, plus the probability of F, this shaded region. But Johnny, what happens in this middle section when I do that?
They overlap?
They overlap. So I counted it twice. So because of that, I need to subtract it out. So it only gets counted once because it got double shaded basically.
Oh, and if it's mutually exclusive, we have to subtract that out.
No, if it's mutually exclusive, there is no intersection. You have two separate circles. If it's
I see.
Yeah. So I mean, you can still use this formula for mutually exclusive. It's just the probability of E and F is 0 if they're mutually exclusive.
Oh yeah, I remember now.
Yeah.
Yeah.
All right, cool. Okay. Well, let me show you guys this in action. So Nick, can you go ahead and read this one out for us, please?
Suppose 2 6-sided dice are rolled, one white and one red. What is the probability that the white die lands on 6 or the red die lands on 1?
Awesome. All right, thank you. So this is an or problem. Okay, so that's the first step, decide and or. Because it's an or problem, I'm going to use my mind map, my formula for the general rule for addition. All right, so I'm going to call white die landing on 6 event A, just for simplicity's sake, and B be the red die landing on a 1. All right, so the first question is, are they disjoint? Well, I would say no, right? It's possible to get both, right? This one is on 6, this one is 1. It is possible to get both. So I'm going to say no, these are not disjoint. So I need to use the full formula, and I do need to subtract out that intersection. All right, so now I want to find the probability of A or B. So I'm going to do probability of A, white die landing on 6. Well, there's only 1 out of 6, right? So that's 1 out of 6. Red die landing on 1. That's also 1 out of 6, okay? And now the intersection. Well, in the mind map, I need to think about, okay, are the events independent? Does the roll on one die affect the roll on the second die? I would say no, right? What I roll on the red die doesn't affect what I roll on the white die. So I'm going to say yes, they're independent. All right, so because they're independent, I can just do the probability of A times the probability of B. And so I do 1 over 6 times 1 over 6 for the probability of A and B. So this is my final answer. All right, so 1 out of 6 plus 1 out of 6 minus the probability of A times the probability of B, since I know that the dies are independent. One does not affect the other. And that is my final answer. Okay, questions on that?
So, Mrs. Leong,
Yes.
so for the subtraction portion, like since because like that intersection is always like, you know, with the Venn diagram, it's always added like twice because of like the two sides of like the two dice in this case, then like you have to like kind of get rid of that, right, in order to like, I guess, avoid, you know, like ruining the actual probability then, or
Right, so you subtract the intersection because that, right, that case of, you know, white die landing on 6 and red die landing on 1, right, gets counted twice. And you don't want to, you know, have those probabilities counted twice. So that's why you subtract that probability.
okay, yeah, thanks for that. Yeah.
Yeah, because the probability of white die landing on 6 and red die landing on 1 is in the 1/6. It's also in the 1/6 here too, the probability of B. So I don't want to count that specific case, that probability twice. So I'm going to subtract one of that out. Okay.
Yep.
I don't know if that clarified things at all. Okay, but I think the diagram, the visual, I think really makes the most sense. It just, you know, that visual of the shading of that intersection twice, and you don't want that. Okay. All right, guys, let's have you try one. I know this seems daunting, but try practicing with that mind map. And I'm going to give you guys that last one to practice, and that way you can see how well you can use these formulas, okay? So this is the question. An electronics store sells DVD players made by 2 brands. Customers can also purchase extended warranties for the DVD player, and the following probabilities are given. Okay, so B sub 1 means that brand 1 is purchased. B sub 2, brand 2 is purchased. And E is the event that extended warranty is purchased. All right, and they give you these probabilities. Probability customer gets brand 1, let's say Sony, is 0.7. Let's say brand 2 is, I don't know, Samsung, is 0.3. So probability that they get Samsung is 0.3. Okay. Probability that they get an extended warranty given they got brand 1 is 0.2. And the probability that they get an extended warranty given brand 2 is 0.4. And your question is just, if a random customer is selected, what is the probability that they purchased the extended warranty? Okay, so give it a shot, look through some of the examples that we did, and test out using these formulas. Okay, test out using these formulas. And I would say building a tree diagram, here's my hint, building a tree diagram for this one could be helpful. Okay, so this is how I would do it, and you guys can let me know what questions and where you got stuck, okay? So first thing I would do is I would set up a tree diagram, because there's a lot going on. There's what DVD player brand did you pick? What did you get extended warranty or not? So this is my tree diagram, okay? So 70% brand 1, 30% brand 2. If they got brand 1, 20% chance they got the extended warranty. So 80% chance they did not. All right. If they got brand 2, 40% chance they got the extended warranty, 60% chance they did not. All right, so that would be my first step. Next, I would focus on, I want to find the probability they got an extended warranty. Oops. So that's this branch right here, and then this branch right here. Okay. So focusing on those two branches, I would do 0.7 times 0.2 plus 0.3 times 0.4. And that would be my final answer. All right, so this is kind of how it looks like in notation form. So to get extended warranty and brand 1, or extended warranty and brand 2. So using that multiplication rule, it looks a little more complicated like this. That's why I like the tree diagram better. And this would be your final answer. All right, so 0.7 times 0.2, right? Brand 1 and the extended warranty given brand 1 plus brand 2 times the extended warranty given brand 2. Since they're disjoint events, I could just add them, no intersection to subtract, and I get 0.26. All right, any questions?